Hi everybody, it's Dr. Burns here, and the next application for derivatives that I want to take a look at is from section 4.2, and it's a topic called the mean value theorem for derivatives. So this is another really important theorem that has a few different applications that we'll see as we go along, and I want to go ahead and show this to you in the video for today. So let's start off with the conditions that are required for the theorem to hold. So it says, let f of x be a continuous function over the closed interval and differentiable over the open interval. Remember, differentiable means it has a derivative. So it's got to be smooth, and of course it's got to be continuous. The theorem says then that at some point in the interval between a and b, there is a specific location where the derivative f prime equals f of b minus f of a over b minus a. And this may look a little fancy, but all this is, remember, is the average rate of change over the interval from a to b. So this is essentially the slope of the secant line that connects point A to point B. Let me give you a picture here, and we've got a graph of a function. Notice this graph is continuous. It's smooth. There's no cusp or anything weird happening in between the interval from A to B. And what we're saying is, if I were to calculate the slope of the line segment, or the secant line, or the chord, as they're calling it in the picture, from A to B, so the slope of that line would be given by f of b minus f of a over b minus a. Then somewhere in between A and B, there is a location where the slope of the tangent line, which of course is the derivative, would be the same as the slope of that secant line. So those two lines would literally be parallel to each other. And that's what the theorem says. There has to be a location, at least one location, where this occurs in between A and B. So our job is going to be to find where that location is. So let's do an example here. It says, given the function 5 minus 4 over x, find all values c in the interval from 1 to 4, so a and b are 1 and 4, such that the derivative equals f of 4 minus f of 1 over 4 minus 1. So make a note that that's just your f of b minus f of a over b minus a. So why don't we first go ahead and calculate what that value actually is. So f of 4, we're going to substitute 4 into the original function, and I get 5 minus 1, which happens to be 4. And then f of 1, if I substitute that into the original function, I get 5 minus 4, which happens to be 1. Just a coincidence that those numbers were the same. So f of 4 minus f of 1 all over 4 minus 1 is going to be equal to 4 minus 1 over 4 minus 1, which just equals to 1 over 1, or just 1. So what the theorem says is somewhere in between A and B, there is going to be a location where the derivative should equal that average rate of change we just calculated, which is 1. So the next step would be to find the derivative of the function. So the derivative, let's figure that out. Remember, f of x was equal to 5 minus 4 over x. Let me make a little bit of space here. So I'm going to rewrite that as 5 minus 4x to the negative first. Of course, don't use a quotient rule or anything like that. Just rewrite that, 5 minus 4x to the negative first. So let me come back down here. The derivative then is going to be 5, of course, that's a constant, so that's going to be 0. Negative 4 times negative 1 gives me positive 4x to the negative second. It's going to be my derivative. So I'm going to set that equal to that average rate of change that I just calculated, which is 1. So then I'm going to solve that equation. I'm going to write that as 4 over x squared equals 1. Multiply by x squared, I get 4 equals x squared, square root both sides, and I get plus minus 2 is equal to x. Now, obviously, negative 2 is not in the given interval, but notice that positive 2 is. So that magical C value that they're talking about is going to be 2. So notice that 2 is in the original interval. So here's a graph of what we're talking about. X equals 1 is here. X equals 4 is here. At x equals 2, there is a location where the slope of the tangent line is equal to the slope of the secant line that connects x equals 1 and x equals 4. And by the way, the slope of that line, remember, is 1. So the value of f prime at 2 that we just calculated is 1. That's what the slope of that tangent line tells us. Now there is a special case of the mean value theorem called Rolle's theorem. So Rolle's theorem says that as long as we have that continuous function on the closed interval and differentiable on the open, and there's one more piece to it, it says if f of a is equal to f of b in that interval, so if the values of the endpoints are equal, then there is at least one number c in the interval where the derivative equals 0. And the reason this happens is because remember what mean value theorem said. It said that somewhere in that interval, there is a location where the derivative equals the average rate of change. Well, if f of a and f of b are equal, then this just simplifies down to 0, right? That's what that numerator would turn into. And so that's what Rolle's theorem tells us, that if those two values at the end are equal, not only do we get the average rate of change, but it actually just becomes 0. So this is really just a special case of the mean value theorem. So let's take a look at a quick example. It says find all values of c in the interval -2 to 2 such that the derivative for c equals 0 on this given function. Notice this is a polynomial, so it is continuous on all real numbers, and of course differentiable. Polynomials, remember, are well-behaved functions. They're always continuous, always differential. So let's go ahead and calculate the values at the endpoints. So f of -2, if you plug in -2 into the original function, -2 to the 4th, I think, would be 16, and then minus 2 squared, of course, is 4. 4 times 2 is 8, so I'm getting a value of 8. And then f of +2, because of the symmetry here, it should be the same thing, but let's just verify it. 2 to the 4th, of course, is 16, minus 8 again, we get 8. So notice that we get the extra condition. F of -2 is equal to f of +2, right? That's the extra condition for Rolle's theorem to apply. So somewhere in that interval, there should be a location C where the derivative equals 0. So I'm going to go ahead and find the derivative. So the derivative would be 4x to the 3rd minus 4x, and we're going to set that equal to 0, and we're going to solve that equation. All of these will pretty much factor unless we're using Desmos to help us solve equations. It should be something we can factor with. So notice I can take out a 4x, and that leaves me with x squared minus 1 is equal to 0. Zero product property, we get 4x equals 0. X squared minus 1 equals 0. We get 0 and plus and minus 1. So actually, if you notice, all of those values are in between -2 and 2. So our magical C values here are going to be -1, 0, and +1. And at all of those locations, the value of f prime would in fact equal 0. And that fits with what Rolle's theorem told us because they're in the given interval. So tomorrow we'll do a little bit of practice with finding these values in class, but we're going to use these two theorems to help us do that. So I'll see you in class.